Today's topic will be moment generating functions. And so, just as a prerequisite, I assume that you know the Taylor series, how to derive it, where it comes from, and also that you know about stats distributions. So, things like uniform distribution, Bernoulli, um, things like gamma distribution, beta, pretty much all the distributions. You don't need to know the specifics, but just the basic ideas behind the distributions. So, first off, what is an MGF? So, an MGF, a moment generating function, there's a couple ways to think about it. Just as a big overview, a moment generating function, there's almost like two kind of basic ways to think about it. One, you can think of a moment generating function as defining a distribution. So we'll go through this later. We'll go through not a proof, but just kind of like an idea of how a moment generating function is unique to every single distribution. So if one distribution and another distribution has the same moment generating function, that means they're exactly the same distribution. All distributions or all distributions have a unique moment generating function. Now, not all distributions will have one. Sorry, to make it more clear, all distributions who have a moment generating function will have a unique, right? One and only one moment generating function. So you can think of it like as a defining distribution. So we can go through like the whole equation for it. It's quite complicated. I wrote this up in LaTeX, but the whole equation is this thing right here. So let me zoom in a little bit. Here we go. So the moment generating function is just defined as the expected value of e to the power of some variable s. S is just like a dummy variable. It's just a placeholder. Uh, e to the power of sx. And x is the actual random variable. Right, yeah. So it seems kind of weird, right? Where the heck did this come from, right? Where did this equation, right? Where the heck does this come from? So we'll do a little bit of a digging in, right? So we have the equation. First off, right? Just to go through like the kind of like the idea behind it. In math, usually, not all the time, but usually we actually, when people make mathematical discoveries, people usually begin with an idea in mind, and then they find the solution, right? But in textbooks, we actually go backwards. We have the solution, right? We have the equation, and then we go through the proof of how we found that equation, right? But usually in mathematical discovery, it goes backwards, right? We have an idea, kind of like an intuition for what might happen, but we do some exploration, and then we figure out the equation, right? So it's the opposite of the textbook approach. So I kind of wanted to try something a little bit new. Um, so the basic idea of how this moment generating function kind of was found, right? So first we know the Taylor series for e to the x, right? E to the x is equal to 1 plus x squared divided by 2, dot, 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 right? And then, of course, expanding upon the Taylor series for e to the x, we get the Taylor series for e to the sx, right? Which is exactly the same. We're just raising s times x to the k power. And then we actually want to now take the moment generating function of the or the Taylor series of the moment generating function, right? So we'll basically end up with exactly the same thing, right? But instead of we'll just have an expected value at the end, right? And we can do this, right? We can do this because we're trying to find the expected value with respect to x, right? So sorry, a little bit down. We're just trying to find the expected value of with respect to x, right? So we don't care about anything else, right? We don't care about s or k. We only care about the expected value of x, right? Because x is the actual random variable. And when we take the derivatives of both sides, right? So if we take the derivative with respect to s, right? So we take the derivative of the moment generating function with respect to s, and we take the derivative of the Taylor series, of the moment generating function with respect to s, right? We see that all the s's basically cancel out, right? So what we get is we basically, since we're deriving, right? We're deriving with respect to s. All the terms, right? All the terms in the Taylor series of the moment generating function, they all cancel out, right? Except for all the values that are up. So like, let's say if we have x cubed, right? We have x cubed. If we take the first derivative, right? The first term is going to cancel out. Um, okay. Oh, to be more clear, if we have x cubed plus x squared plus x plus 1, right? X cubed plus x squared plus x plus 1. If we take the first derivative, right, the 1's going to cancel out, right? If we take the second derivative, x to the 1's going to cancel out, right? If we take the third derivative, right, x squared's going to cancel out, right? It's every time we take a derivative, right, the smallest term is going to go to 0, right? It's just going to become 0. And so that's all I'm saying here. So it's going to be equal to 0 plus s times expected value of x s squared divided by 2 times expected value of x squared and dot dot dot, right? So on and so forth. But then, since s is a dummy variable, right? S is just kind of like a placeholder variable, right? It's just to make the derivative easier, right? We just have to take it with respect to something, right? So s is like a placeholder variable, right? So if we set s equal to 0, because of how derivatives work, right? If we have like if we have x cubed plus x squared plus x plus 1, if we substitute 0 for x, right, all we're going to get is 1, right? If we take the first derivative, we're going to get 3x squared plus 2x plus 1, right? If we substitute 0, we're just going to get 1 again, right? So every time we take a derivative, we're just substituting 0 for x. Or s, sorry. Substituting 0 for s. In that way, everything else cancels out, right? So it's going to be 0 plus 0 plus 0 plus 0. Everything cancels out except for the value that's the actual... everything cancels out except for the x to the k power, right? So everything cancels out that's not the same power as the derivative we're taking, right? So if we're taking the fourth derivative, everything except the x to the fourth cancels out, right? So we're only left with x to the fourth. If we take the seventh derivative, right, everything becomes 0 except for x to the seventh, right? So we're just going through this whole process, right? So we started with this moment generating function, right? We didn't really know where it came from, but working with it, right? We can see that if we take the derivative, right, the nth derivative of the moment generating function, we get the nth moment of the distribution, right? So if we take the first derivative, we get the first moment. If we take the second derivative, we get the second moment. If we take the third derivative, we get the third moment. And just to reiterate, there was one thing that I have to point out. A moment is just defined as the expected value of x to the k power. It's just the expected value of x to the k power. And so, right, at the very end, all we're left with is kth derivative of moment generating function is equal to the kth moment. So it's basically, this gives us kind of like two ideas behind what the MGF is actually doing. First off, the MGF is basically, it's called the moment generating function because every derivative generates a moment, that specific moment that you want to find. And second, the MGF actually encapsulates, right? It gives you all the information for all the moments, right? Because it's because it's e to the x, we can make a Taylor series, right? And because we can make a Taylor series, it's actually just adding up all the. It's the sum, the moment generating function, the MGF, is just the sum of all the moments multiplied by some, multiplied by the Taylor series coefficients. The polynomials, this should be coefficients. But yeah, multiplied by the Taylor series coefficients. So that's the really, really cool thing about the MGF. So now if we go back, right, kind of to figure out intuitively, like how did people figure this out? Well, first off, people kind of wanted to I don't know all the history behind it, but people wanted to figure out how to describe statistical distributions, right? All of them, right? If we have one distribution, right, is there a way to compare it to another distribution, right? Is there some sort of way to like add them together, subtract them, multiply them, right? Because in the real world, there's a lot of distributions affecting each other, right? So that's a really, that was a kind of a pressing question, right? You want to find a way to compare, contrast, and actually modify distributions with each other, right? So that's what people were kind of thinking about. And then came the idea of moments, right? So to be a little bit more specific, the moments just determine typical ways to describe a distribution. So for example, if I go to way up high here, the first moment is just the mean, right? It's the average, right? Since the moment, right? Moment is defined. Let me write it down very clearly. Since the moment equals expected value of x to the power of k. So this moment is equal to that. The first moment is just the expected value of x to the 1, right? The nth moment is equal to the expected value times x to the n. So the first moment is just equal to the expected value of x to the 1, right, which is just x. The expected value of x is just the mean, right, the average. So the first moment is just the average, right? The second moment is the expected value of x squared. And x squared is, it actually gives you the standard deviation graphically, what that's saying is if you take all the outputs, right? If you take all the if you take the probability, if you take the output of the probability density function, and if you square all the outputs, right? So if you have like if you have a coin toss, right? If you have a coin toss, there's a lot of ways to define it. You can do like 0 and 1 for heads and tails. So for the graph, right, you would just have a bar graph, and you would have a 0 for heads, let's say, 1 for tail, and each of them would have a probability of point, no, 0.5, right, half. And basically what x to the power of n, what that's saying is you're just squaring all the x values, right? So you're so x is the random variable, right? It's the actual outcome. So it's you're squaring 0, so 0 squared is 0, and 1 squared is 1. So in this case, you wouldn't get anything different. But let's say you're rolling a dice, for example, right? So it's only possibilities for 6-sided dice, right? 1, 2, 3, 4, 5, 6. Those are the only possibilities for x, right? For random variable x. If you have random variable x squared, that's just going to be all the outcomes squared, right? So all the possible outcomes for x are 1, 2, 3, 4, 5, 6. For a dice, right, you can only get 1, 2, 3, 4, 5, 6. For x squared, it's just 1, 4, 9, 16, 25, 36, right? Those are the possible. That's x squared. X cubed, right? You just cube it, so on, right? But you don't square the probabilities, right? Probability remains exactly the same. You just square the actual possible outcomes, right? You just square the number you get on the dice, right? You just square the whatever the outcome of the random variable is, right? Graphically, that's what that's saying. Now, there is one point I have to mention. We mentioned earlier that the second moment, right, gives you standard deviation, right? Actually, it gives you second moment gives you this the second the second raw moment doesn't give you standard deviation. The second central moment gives you standard deviation. What's the difference? All you have to do is just shift the location with respect to the mean. So instead of graphically, all that's saying is basically you're just shifting by a certain amount. So for example here, let me go to the normal distribution. You're just shifting by the mean, right? So let's say the mean is like at negative 5, for example. If it's at negative 5, the standard raw, the second raw moment doesn't really let you know anything about the actual standard deviation of the distribution. When you get a central moment, all you're doing is just getting the moment when you basically change the center, right, to be from when you change the you don't change the mean, but you just shift the mean, right? So you do x minus mu. That way, when you have the mean, right, when x is x is the random variable, and mu is the mean. If you do x minus mu, you're going to get the random variable minus the mean. So at the mean, right, you get mean when x, the random variable, is equal to the mean, right? It's just going to be mean minus mean, which is 0, right? So you're just you just centerize, I don't know if that's a word, but you just center the distribution, right? So that it ends up at 0. For example, with the dice, right? With the dice, you have 1, 2, 3, 4, 5, 6. But if you do x minus mu, right? If you do x minus mu, for 6-sided dice, right? The expected outcome is 3.5, right? It's just 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, right? That's 3.5. So since the expected value is 3.5, right? You just shift everything, right? Do you x minus 3.5, right? So you get, instead of 1, 2, 3, 4, 5, 6, right? As the possible outcomes, you just get negative 2.5, negative 1.5, negative point half, 1/2, 2/2, right? Those are the new outcomes, right? For the shifted distribution, right? So all you're doing is just shifting. You're just shifting this distribution back and forth. Centering means just it's at 0. It's centered at 0. For the third moment, you actually get something called skew. It's just how heavy the weights are on the left or the right. It's not how equal or centered something is per se. It just shows you how skewed to the left or right. You can, for a bit more technical thing, you can still be unequal and have 0 skew, right? So the left and the right sides are balanced, completely balanced, but it can still be non-symmetric, right? Asymmetric. All symmetric things will have also, so like the normal curve, right? It's completely symmetric. The normal curve has a skew of 0, right? All symmetric curves have a skew of 0, but you can be non-symmetric and you can still have a skew of 0. So it just shows you how left or right sided the graph is. Kurtosis, it just shows you how tail heavy distribution is. It doesn't tell you how center heavy something is. It just shows you how tail heavy something is. So just to kind of show this graphically, I made this little program, very simple, but it just shows you kind of how the graphs of each moment looks like. So there aren't any labels, but as you can see, the green one just shows you the standard deviation. The yellow one shows you the skewness, and the blue one shows you the kurtosis. Let me see if I can make it a little bit more skew, just to make it a little bit easier to see. There we go. And here we go. So with this, you can see that this yellow part is showing us where the mean tends to be. This blue part is showing us where the standard deviation tends to be. And here, just a couple more. Just need to do a little bit more debugging. But here we go, boom, boom. Just to make it easier to see. Here. So if we just have the mean and standard deviation, this is actually just showing us the distribution of the standard of the second moment. So as you can see, all we're doing is just squaring all the outcomes we don't square the probability, we just square the outcome. So we take all the values here, right? So all the 0, all the 1, all the 2, and we square it, but we just keep the probability the same. So if we just square all the outcomes, right? -3, -2, -1, the 0, 1, 2, 3. If we square all the outcomes, and then if we just add the probabilities together, this is what we end up with. So this actually shows us the second moment, the actual distribution of the second moment of the normal distribution. Right? And if we take a look at this, right, expected value, yeah, it looks like to be about 1, right? There's a lot of values at like 0.2, 0.1, 0.2, but since that's since most of those values are very small, if we just take a look at the curve, right, see where about where half of the roughly half of the probabilities lie, it's about 1, right? And that makes sense, right? Because the standard deviation of the normal distribution, it's 1. In this case, I set it to be 1. Yep, right here with the standard deviation. So that just shows you kind of like how the actual distributions look like for now, for kind of like the big idea, the big intuition behind moment generating functions. So we have this problem, right? We want a way to describe all distributions, right? All gamma distribution, exponential, beta, normal, right? We want to describe all of them together at once, right? How can we do that? And then we've got these descriptions, right? We've got mean, we've got standard deviation, skewness, kurtosis, right? So on and so forth, right? And then what people kind of eventually found out, right, is with a continuous distribution, there's actually a really neat way to describe it, right? When we take a look at the Taylor series, right? When we look at the Taylor series, we notice that you can decompose any simple function. We can decompose any simple function into polynomial, right? X squared plus x cubed plus x fourth, right? And that's a super duper powerful idea, right? So in this case, we have sine of x, right? We can describe sine of x. We need infinite polynomials, but we can describe it, right? And of course, with the Taylor series, right, the basic idea is at that specific center, right? In this case, the center point is 0. At that specific center point, the equation is going to be equal to the Taylor series, right? So the blue line, right? The blue lines show you the approximations, and the yellow line shows you the actual function. And you can see that at the point 0, right, where we center it, it's exactly the same value. So I like to think of Taylor series as like you're putting a pin, right? You're putting a pin on that exact point, right? So you're fixing that point, right? You're fixing that point, right? So at 0, boom, you put a pin. Everything else on the function can change. You just can't change that point, right? And every time you take the Taylor series, each term in the series is equal to the derivative of that series of the function you're trying to approximate. So, for example, with sine of x, right? In this case, when we're trying to approximate it, the first term of the Taylor series is equal to the 0th derivative of sine of x, right? The second term is equal to the first derivative of sine of x, right? So on and so forth, right? So all the derivatives basically equal each other. They line up. And because of that, right, there's a unique way to describe all simple, technically it'd be called analytical functions. Right, so the neat thing about that is we can describe almost all functions, right? So in this case, we have another Taylor series. We have this certain function, right? This bold in yellow. So the first order doesn't really approximate it that well, but the second one, getting closer, the third one, getting closer, and so on and so forth, right? And we, because I set the center at 0, all of them, right? All of them, they're equal to each other at exactly 1 point. It's 0. So now, right, if we have this idea of the Taylor series, right, we can describe any function. Right, now things get interesting, right? If we can describe any function, any analytical function, is there a way to describe distributions, right? Distributions using the Taylor series, right? And people probably thought about this for a while. And the answer people eventually came up with is the moment generating function. The proof for why every distribution has a unique moment, the proof for that is it's a little bit beyond the scope of this video. It's quite complicated. But kind of like intuitively, what we're doing with a distribution. So we have the normal curve, for example, right? Intuitively, what we're trying to do to figure out like a unique function for the distribution, right? Number one, we know that since it's continuous, right? All continuous distributions have they're smooth, right? They have a smooth curve. And second, we know that we know that it's possible to, because it's smooth, right? There must be some sort of derivative operator, right? We can take on the curve, right? Taylor series. But then third, right? The biggest trick really is to actually use the expected values, right? The expected values in order to figure out the equation for the moment generating function. And the biggest thing that helps this idea is the fact about the probability distribution itself. A probability distribution, right? The area under the curve, right? Total probability has to equal 1, right? We don't have 101%, right? We always have an area of 1 under the curve, always. There's no other trickier distributions, but in a standard distribution, right? Probability always equals 100%, right? Which means when we try to find like an equation for it, we're always gonna end up with a unique way to allocate area under the curve, right? If it was, right, if the area under the curve could be any number, right? If it could be 0, if it could be infinity, right? If we had infinity area under the curve, right, there'd be no, I don't know of any way, I know there might be, but it'd be a lot trickier, right? A lot trickier to find a way to describe it, right? Because with infinity, right, there could be all sorts of possible shapes and sizes, right? There's no way to bound it, right? But since the area under the curve is 1, right, we know that for sure. That also means we know that the Taylor series, right, the sum has to add up to 1, right? The integral of the area under of the curve, sorry, the integral of the curve has to equal 1, right? Now the distribution could be, right, the distribution itself could be going to infinity, right? Like a geometric distribution, right? Uh, you can roll, let's say, what's the chance of getting no heads, right? In 50 tosses, right? Very 2 to the, no, well, half to the power of 50, right? It's very, very low. Still possible though, right? So some distributions have infinite tails, right? They have probabilities to infinity, but the area under the curve is still 1, right? It's still 1 no matter what. So because of those two facts, right? The distribution is smooth. Number 2, the fact that the area under the curve is equal to 1. With those two facts, now we can use calculus, right? Calculus skills. And because of those two facts, intuitively, this isn't a proof, not a proof, but intuitively, every curve, right? Every curve which has an area of 1, right? That's smooth, right? If it has the same sort of shape, right? Quote unquote shape, right? It has to be exactly the same distribution, right? It has to be. If it had a different curve, right, it would be a different distribution, right? Because of those two conditions, right? Because it's smooth and because it has an area of 1, right? Because of those two conditions, if it has the same exact equation describing the curve, it has to be the same function, right? So now, you know, pretty much the last step to connect all those ideas together is the fact that just like in this kind of like the proof of why moment generating functions will generate moments, because of how e to the x works, because of the Taylor series for e to the x, you know, if we keep taking the derivative of the moment generating function, right, all we get are the moments, right? Exact raw moments. And that's pretty much the final kind of like it's a leap, but it's like the final step to figuring out why the moment generating function actually works. So now with that, I just kind of wanted to show what these moments actually do. So the mean, right? The first moment, the mean, it just shows you where the distribution is placed, right? It's just shifting it left and right, right? So if the mean is at -7 or -10, that it's just going to shift to the left. If it's positive, it's going to shift to the right. That's all that the mean is doing, right? It's just shifting this distribution. That's what it looks like. The standard deviation, it just shows you scale, right? How wide or how narrow, right? So we can make it a lot wider or a lot narrower, right? Narrower. That's all that standard deviation does, right? It just shows you this scale. And then skewness and kurtosis are a bit trickier, but skewness, like I mentioned, is just how heavy one side is compared to the other with respect to the origin, right? So if we take the center, is the left heavier than the right side, or is the right heavier than the left? That's all that skewness is doing. And kurtosis is how tail heavy it is. Are the tails heavier than the center, or not? That's all that kurtosis is checking. So with that, that's the video for moment generating functions. And it took a while, a long while to make this video. I'll post a link to the Python file, so you can kind of play around with the distributions. I'll post a link to the LaTeX file so that you can see the actual equations, the work for it. And I'll post a link to all the resources that I use for this video, including the proof for the uniqueness of the moment generating function. I hope that made the idea a little bit more concrete. The moment generating function can be a pretty abstract idea. It seems like it's just thrown out of nowhere at first, but going through the derivatives, right, deriving the moment generating function, we can see that it actually does generate moments. As the name says, all we have to do is take the derivative.